So, we now start as promised the Quasi-Newton methods. We will see the homeworks later on. Now, if you go back and remember your Newton's method that we have discussed, then in Newton's method what we had essentially wanted to say is that instead of taking the instead of looking at the problem the function f itself at the point x k current iterate, I look at a quadratic approximation of that f, and then I try to study the problem by trying to minimize that quadratic approximation, and that gives rise to what is called the the Newton equation, Newton iteration, which I write as so this is, as you know, we recall that this is what is called the Newton iteration. Now, I can look at it from a very different point of view. What essentially I want while I am trying to solve an unconstant optimization problem is to solve this equation that is find some x star in Rn such that the gradient of f x star is equal to 0. A more general problem can be that take a function from Rn to Rn, find x star or x bar such that f of x bar maps to the 0 vector. Now, this how do I do, because we already know that equation solving, you learn about Newton's iteration essentially when you try to learn in calculus how to solve functions f. If you have a function from R to R, say f tilde, then you want to have f tilde x equal to 0. So, you want to find the x here. So, there you learn about Newton or Newton-Raphson method, whatever you want to call. Now, how do, the question is how to, if you are when n is strictly bigger than 1, the question of course is how to find the solution of this equation. Now, essentially I can now apply the same logic here, okay, but only the important thing in optimization is to know that every iteration the function objective function value decreases, that we will fix up by fixing a descent direction. Now, if I have, suppose I start with a point x naught, so x naught is my starting point, starting point. Suppose f x naught is not equal to 0, then I must move from x naught to some x 1. How do I do that? So, I can write the Taylor's expansion for functions from Rn to Rn, vector valued functions. So, f of x 1, the next iteration, f of x naught plus the Jacobian mapping, which I am writing at as f dash x naught, which actually if you want to be truly erudite and everything is nice, you should write this as Jacobian of f at x naught. So, I am just writing this as f dash x naught, and then I have x 1 minus x naught. So, I have made a Taylor's expansion, but it is not exactly a Taylor's expansion, because I have ignored the error term. There is some error term here which I am ignoring. Suppose I can do this, that is if x 1 is somewhere very near to x naught, possibly I can write it in this form. Here this is the matrix. Now, technically this should be a number between, there should be a vector between x1 and x0, but okay, we are just, or we should just briefly write, if you do not want to write equality, you just can think of that I can write fx1 approximately, I can write it as this. Now, once you can do that, then you observe that now I want that x1 to be my solution, that so if x1 f of x1 is equal to 0, it would imply that we can approximately, and hence we can just, for getting the approximation for a certain time, you can have this expression which will lead to provided you can make a inverse of this matrix. Now, just put f, capital F, as your gradient of f, and then you get the Newton iteration. So, now what I do that, okay, if I can do this sort of thing, when I want to move to the case where I need not have these to be positive definite at every xk, then I try to do something else. That else is as follows. Now, instead of writing fx1 in terms of the this derivative, I bring in some bk, which is a positive definite matrix, and I write, because here I would have really needed here in this case I would have really needed a positive definite matrix. So, I can replace this by a positive definite matrix. So, if I had a positive definite matrix, then if f dash x naught was positive definite is PD, then it is invertible, you have got, you get this, right. And then it is very important that now what I do, I will make this sort of approximation. So, what I have is some PD matrix into is an n cross n symmetric PD matrix. Is an n cross n symmetric PD matrix, positive definite matrix. So, once I do that, it is very important to note the following. Now, I can write, suppose my x1 is my, if fx1 is equal to 0, then I can write x1 minus x naught minus b naught inverse the f here. So, this is a very good scheme, a quasi-Newton scheme, a quasi-Newton scheme for equation solving. So, I have replaced the, because here I needed an invertibility, which I cannot guarantee of the Jacobian every time. So, so at every moment now, when I go from b naught, at every iteration when I go from x1 to x2, I have to have a new b1 which will be used to make the jump from x1 to x2. So, it is a quasi-Newton scheme for equation solving. Now, if you look at that, what happens is that I can write more general thing as xk minus xk plus 1 minus xk is minus bk inverse f of xk. But I am making too much of an assumption that I will take a PD matrix. Suppose I do not take a PD matrix, then I can write this thing in general as this is one way of writing the thing. So, essentially I can now make a more nicer thing, because I have already assumed that x k plus 1 is 0. At f x k plus 1, if it is 0, then I get this equation. So, it does not harm if I write this as, because this is 0. So, from x k to x k plus 1, I come with the presumption that possibly x k plus 1 is a solution. So, if not, then it will not have a 0 value. So, this would be the iteration that I will use. So, now if I put capital F as grad f, what I have here is that if I take some B, some other matrix which I do not bother, then okay, it could be a positive definite matrix, and then you can put a BK, that is a you could get this iteration scheme, which is the Quasi-Newton scheme. So, there is something I can write. I can write this as grad f x k plus 1 minus grad f x k. This is sometimes called the secant equation or the Quasi-Newton equation. So, if I put S k as x k plus 1 minus x k and y k as grad f x k plus 1 minus grad f x k, then I can write this thing can be now written as b k s k equal to y k. Now, actually the Quasi-Newton iteration for the optimization problem can be written as, because I am expecting this, I will update from B 0 to B 1 in such a way that all the B k's would be positive definite, and so you will have an inverse. Sometimes we need not bother about even computing the inverse, we can take an approximation of the inverse itself. So, this one is the Quasi-Newton scheme. So, also observe that if I have kept b k plus 1 s k is equal to y k, then because b k plus 1 is positive definite, we will have s k b k plus 1 s k is equal to s k y k. But now this is strictly bigger than 0, because this is P D. So, in general we will always assume B naught to be P D, because that will help us, but even if you had not assumed P D, you could have still replaced the gradient by some Hessian by some matrix and could have got this equation. Okay, but we will just continue that we are only taking symmetric P D matrices, all these B k's are symmetric P D matrices. Now, the interesting thing that we really need to look in here is that now this would mean that this is strictly bigger than 0. So, this is sometimes called the curvature condition. Which is guaranteed when B is positive definite, which is not guaranteed when it is not. So, when f is strongly convex, such a thing would actually occur, but the curvature condition holds. So, this goes as your homework for this part. So, essentially now observe that if I take dk is equal to minus bk inverse grad f x k, where B k is symmetric P D, symmetric positive definite, then d k is a descent direction. Then d k is a descent direction, in the sense that if you write grad f x k into d k, this is nothing but minus now, because B k is P D, its inverse is also P D, positive definite. So, this part without the minus would be strictly greater than 0. So, the whole thing, this one is strictly less than 0, implying that. So, the important question here is not important question here is how do I update the matrices B naught. So, if I know B naught, say usually the B naught, the starting one is the identity matrix, because we know that it is anyway positive definite. Then I have to go from B naught to B1, B1 to B2 and so on, Bk to Bk plus 1 and so on. Let us stop. The question is how do I make these updates. So, how to make an update from Bk to Bk1, Bk plus 1. The question is how to do this, and then if I want to do this, this Bk plus 1 also has to remain, this one has to remain PD, positive definite. Positive definite when I already know that Bk is symmetric positive definite. Of course, it has to remain symmetric PD, which I am not writing every time, but okay, like this I will write in short that. Now, how do I find that, right? So, हम cut करो कितना हुआ 4 minutes. Now, suppose I want to get a new B, right. I know the Bk and I have to get a new B. So, what should that new B do? The new B should at least be symmetric and satisfy the same sort of equation, that is basically I am expecting the new Bk plus 1 the same sort of thing that we had just figured out. So, this is the equation Bk plus 1 has in terms with xk and yk. So, k plus 1 and k is linked through this so called second equation. Now, what I am trying to say is that if I want to find a Bk from Bk, if I want to find a Bk plus 1 must be symmetric and must satisfy the second equation or the Quasi-Newton equation. Now, what we want is that there should not be a huge change between Bk and Bk plus 1, because we want to also reduce our computational effort. If there is a huge change between Bk and Bk plus 1, then that is not fair. So, what we really do is we want to find the Bk plus 1 through finding a problem of minimization in terms of matrices. So, when I have a Bk, so I now want to look into this particular kind of problem. So, I have to find the B that will minimize this norm, the difference between the norm, which I will say what sort of norm we will use in the next class. So, I have to have this, the Bk plus 1 should be satisfying this, the B, and it has to has this. So, basically I want to now use this approach to choose my B. So, the thing is choosing different sort of norms, I would be able to choose a different sort of B, which will be all PD. So, tomorrow's class will discuss how to compute the B. And that would again take us back to the Karush-Kuhn-Tucker conditions and the Fridtjohn conditions that we have learned. So, and we will talk in detail about the type of norms etc., that is used here. So, we will now try to solve it, maybe we will look into first a more simplified version of this, but then try to apply it here or part left as homework. So, the question is now how to compute the B, and that is exactly what we are going to discuss in the next lecture. Thank you very much.